If we go minus 1.65 of these, we're gonna get the other 45% on the bottom side, and that's gonna leave us 5% chance of getting it wrong on the bottom, 5% chance of getting it wrong on the top. But we're good with that for now.
So wait, 1.96, is that the standard error?
Which one? This?
Yeah.
This?
No, that's just the standard deviation.
Standard deviation. It is, did you say standard error? You said standard
Yeah,
error.
that's
That's right.
correct.
Yeah,
That's correct.
that's right.
Looking for
Okay.
95, so it's 1.64, that's 5. Why on this one, you put the higher one, over 90?
You take the more extreme one, the one further from zero. You can use either. You can use either. Once you just get more comfortable with it, that's when you'll say, oh, okay, more extreme one, we can get a little more precise. Okay, so let's multiply 1.65 times our standard error, and let's add and subtract that to our 0.24 estimate. So our confidence interval is going to be 0.24 plus or minus 1.65 times 1.9%. We could have just left this as, yep, 0.019. And does anyone still have it in the calculator? Did you calculate it? Long since gone. All right. Let's, if we could go back, let's do this calculation. The 1.65 times the 0.019.
0.031.
031. Okay, yes, and actually it's in the textbook. And that's what it says. So this we could call our margin of error. Alright. So our 24% plus or 24% plus or minus 3.1%. Alright, so 24% minus 3.1% is going to give us 20.9%. Okay? Let's be consistent with whatever it says in the book.
209. 0.209, yeah, 20.9%. So 27.
That's right.
That's right, okay, alright. And what do we have on the upper side?
27.1.
7.1%? Alright. So now, one thing I'll say, so our confidence interval estimate, we're 90% sure that the true population proportion is between 20.9% and 27.1%. Does this make sense?
That's what I'm saying.
Alright, and we've got the exercise to, yes.
Okay, so do we have to find, because if we find the left side, is it always gonna be the same number as the right side?
Yeah.
So we don't have to do, okay, that's right.
Yes, Gabe.
Can you go back to the first part of the problem where you got the 0.24%?
Yep.
Is there a formula?
Yeah, this is, so remember we asked 500 people, and 120 of them said, yes, we support the change.
That's the percentage of
120 divided by 500, 0.24.
I mean, is there a formula? Like,
Oh, yeah, the percentage, it's 120 divided by
So
500.
the sample is 500, right? 500 out of the entire population.
Yes,
Okay. Could be a million, could be 100,000, like whatever.
yes. Okay, let's move on to another one. Question, yes.
Really quickly.
Yes.
On the quiz, you caught me off guard last week. How would
Probably would have.
how would we word that? The proper way to word
We
it.
would, okay, so I'll answer that two ways. One, I'll answer how you would word it, and two, I'll answer how you would put it on the quiz. How we would word this is we would say, after our analysis, we are 90% confident that the true population proportion is between 20.9% and 27.1%. And all you would write on the quiz if I asked for the confidence interval is just this.
That's it?
What?
That's what I
Well,
was.
like, I'm talking about like
Question
the
number
multiple
one.
choice, you know, it's like, what's the proper way?
Oh, yeah, we'll go back to that. There was one tricky multiple choice one. We'll talk through that one at the end of class, if anybody wants to. Alright, okay. Let's look at page 282, number 18. I'm gonna let you all work this one yourselves for a minute, and then we'll come back together as a class. And yes, number 18, this is, yeah, full-time employees, how many are technology resistors? 283, number 18.
So quick question, so if this number we rounded to this, and we got this as our answer, would that still be okay?
Like I said, I would leave this in your
So
calculator.
long, okay.
Because this is a whole percentage. And so, if we were to round that, we could go up to a whole percentage or down. Oh, this is the
Yeah. If you left the long number,
Yeah,
so it would come out to.
you can round it here. Yeah, round it to 2 decimals. Here.
You say they're number 18?
Yes.
Yes.
We need the chart. The
Yeah, well,
583.
586.
Or make it open it. It's all here. I'll bring it down.
Over Z-score?
He says to leave it, and then go back to it. Cause when I did. And I feel like it was more. And the answer.
This one?
Can I see the table with the conversation?
Look, this one. It's the same thing. Sorry.
Oh, no, it's okay.
So that's the standard norm.
I can just find it on the book. 568.
That's my.
Thank you.
The math is easy, it's just how to send out the stuff.
Maybe we just want to- This is
Out of 100?
Yes. Proportionally.
Oh, yeah, so 1 minus 0.09 is 0.91.
Oh, yeah, we have the 120.
So on the quiz, we have to say margin.
I think I only asked for confidence intervals. All right, we ready to work this one as a team? Not yet, okay, take it back.
Yeah, they're the same thing.
That sounds right.
So that means, oh, it's actually 1.5, right? Yeah, I think it's 1.6.
Alright, let's give it a shot. Two more.
Let's ask her if she got the same thing. Did you get 1.96 for this school?
Yeah, okay. Wait, okay, boom. So point 20, point. Plus
And we have the 98%.
Minus 1.8 times.
I have it in that spreadsheet.
So,
Put in percentage, just be clear. Percentage sign. Alright, so let's work this one. We can take some time with it if you still haven't finished. We can just make sure you're comfortable with this example. In this situation, we're trying to find the percentage of technology resistors. Maybe we're trying to sell some sort of technology product. Maybe we're trying to see how some sort of software might be received. So we take a sample, these 901 employees, and we find 9% of them are resistors. That is just our point estimate. We want a confidence interval, so when we go to the investors, we can say we're 95% confidence, this is the true proportion, so invest in our software to help these people. We need to do two things to start off this problem. One, we need to find the standard deviation of the sampling distribution of the sample proportion. Two, we need to look in the back of the book to find how many standard deviations. We need to go plus or minus our point estimate to be 95% confident. So, standard error is going to be our 0.09 times 1 minus 0.09, it's going to be 0.91, divided by 901, square root of that whole mess. Yeah, definitely square root it. What do you got? 0.0095, I like it. Alright, the other thing we need to do is find the appropriate z-value for 95% confidence. Plus or minus what?
1025.
is it 1.96?
Oh, the z-value 1.96.
1.96?
Plus or minus 1.96. Excellent.
Yeah.
So, our answer is going to be 0.09 plus or minus 1.96 times standard error 0.0095. Alright, let's calculate this and call it margin of error. Anyone have this for me?
0.01868.
868. Excellent.
0.01.
So 0.01. So that is about 1.9%. Right?
Yeah, so
Alright, confidence interval, what's the lower bound going to be? If we take 0.09 minus this,
0.07130.
1, 3, okay?
Okay.
And what's the upper bound? So not 0.0, it's gonna be,
0.10868.
8, 7, okay.
And then to make it percentages, it's gonna be 7.13% and 10.87%.
Yes, this could also be written as 7.13% and 10.87%.
Oh, 88, I mean,
Yep.
7.9.
Sure.
Can you just, instead of just going ahead and doing the 0.09 plus minus 1.96, can you just go in straight into the margin of error and just start multiplying the 1.96?
This times this?
Yeah, I mean, you're doing it there, but like,
Oh, yeah,
I mean,
you mean not even writing this out?
like say if I did that on a quiz, if I just kind of skipped that and just did everything straight through,
Yeah,
and got the 0.0186, that'd be fine?
yeah,
Okay.
that'd be fine.
Yeah, I did that.
Just find
I
this
mean,
is-
I guess this would make a lot more sense just so you can keep step by step.
Yeah, just find a way that doesn't confuse you and works for you.
So that's the margin of error, right?
This, yeah,
The 0.018.
yeah. Margin of error.
So where would you use the standard error?
We calculated the standard error, is 0.0095.
Right,
And
okay.
the question
The
is.
standard error, okay, I get it.
I got it.
Yes, Gabriel.
First, I need help with the Z guy.
Yes. Okay, so, actually, I shouldn't have erased this. Do you remember, I had the answer to your question right here. It was, so let me go back to the slides. All right, so, if we were to conduct 1,000 sample means, or sample proportions, they would fall into this nice, beautiful, normal distribution bell curve. 68.3% of them would be within 1 standard deviation of the population mean. 95 would be within 2, 95.5 would be within 2. So 95.5 would be within 2. The question is, how many would be within 95%? It's a little bit less than 2, right? How much less than 2? Okay, so we say, well, if we're 95% confident, that means 2.5% of the time, this proportion, right now it's 9%, is gonna be too high. 2.5% of the time, it could be too low. So what z-value is associated with these numbers? I think the easiest way is to look on the negative side first. On the z table in the back of your book, on the left-hand side, find the area under the curve that says 0.025. And if you look, you're going to see that's negative 1.96. And as Andrew pointed out, you don't even have to do the other side, you can just assume it's going to be identical, positive 1.96. If you wanted to though,
So, when we see 0.0095, so we're not gonna take 95%, right?
this is 1%. This is 1%. 0.0095 is pretty close to 1%. Let's do some more examples of that. If I were to write 0.012, what percentage is that? I'm 1.2%. Yeah. If I were to write 0.50, What percentage is that? Yes, 50%. If I were to write 1, what percentage is that? 100%. Yes. So, don't get confused. You can either put a percentage as a decimal, or you can call it percent. Percent means per 100. So 1.2 per 100. Are you making, is this one making sense? We have an optional proportion one we could do, or we could move on to the next step. You want to do the optional one?
Yeah.
All right, let's do it. Page 282, let's do number 12. Please take a look at that one. Let's work that for maybe 3 minutes, and then we'll get the answer as a class.
Random samples, are we doing anything different than instead of random samples?
No, random sample is good. We like random samples. All right, are we ready to try it? 2 more minutes, okay. Take your time. How you coming?
The Z value? That's what I was trying to find, it should be the same as before. I just don't know how to get it there.
Would it be the 10, the 10
Yes.
divided for 5?
The Z value?
Yeah, the Z value, right? Because we have 10%, right?
Alright, I don't know.
Where would you find 10%?
All right, let's try this one. So we're sampling. Say we want to know the percentage of people in this town who might buy our product. And we ask them, you know, would you have need of this? And 65% of our sample say yes. That's just an estimate. We need a better confidence interval to tell us, and with a, I guess, a higher degree of accuracy, what that actual proportion is for the whole town. We sampled 100 people, and we need two components. We need standard deviation of the sampling distribution of the sample proportion, also known as standard error. And we need the proper Z value. For the standard error, we're going to take 0.65 times 0.35, 0.65 times 1 minus 0.65, divided by n, which is 100, square root of all of that. All right, who's got that for me? Just blurt it out.
0.0476.
0.0476, is that right?
Yes.
Excellent. So we've got a standard error of about 5%. We need to know how many standard error pluses, how many standard error minuses we need to go to be quote-unquote right 90% of the time. All right, so how many standard errors do we need to go plus or minus to be right 90% of the time? 1.65 plus minus.
How do we get that?
1.65?
Yeah.
Yes. So
Which one? You have that.
So, before we even go to the 1.65, I'm having problems with the math part. Where did we get the 0.0476? My calculator is not working the same.
0.65 times 0.35.
I did that.
Divided by 100.
Did you get?
Take the square root of all that.
Did you get plus?
So there's, I got 0.002275 inside the square root. So what's the number?
Now, once you wanna find the
I
margin
gotta
of
see
error.
each.
Do we like this? This is right, right?
Yeah.
Okay. Yeah. So are you doing on Excel, Nellie?
Make sure you don't think it goes smart.
No, I was doing it on this calculator here.
On the chart.
All right, I'll just copy it and I'll take it from there.
1.65.
Okay.
No problem. No.
Alright, so 1.6.
All right, is that the right?
Like, how do we get it?
Got it.
Alright, so for my, I mean,
You know?
I know the concept, I just don't,
Looking at it later.
I know that it's only 1.65 standard deviation.
I don't know. That's what's wrong with my
So we need to be 90% sure.
That's not what we do.
Alright, so that means, what is the percentage chance that this estimate could be too low outside of the 90% confidence? 10% chance total of error. 5% chance of too low, 5% chance too high. So since this is normally distributed, we can use all this beautiful stuff
And
here.
it's this table.
Yep. Yep.
And then we look for process and.
Yeah.
Which gave you.
This is already knows.
Yeah, you see the line between there and there.
Okay, so that was the problem.
Well, yeah, use the more extreme one.
That doesn't give the whole thing in it.
Yes.
Yeah. See what I like?
Right?
Yeah, I know why.
Oh.
Me, right? And I know the,
I forget to add
I
those.
know the,
So this is probably for this, for my,
1.49.047.
I can't.
49.
Alright,
I gotta take one.
so we have calculated our standard error. We know how many standard errors we need to go, plus or minus, to be quote unquote right 90% of the time. So let's do that, 1.65 times the standard error gives us what?
0.07854.
Oh, I'll show you in a minute.
Excellent. That is our margin of error. Alright, and if we add that, so that's about 8%. So what's the lower end?
57 point, I got 0.13%. I kept the long number.
Yes, I like it.
And then the higher is 72.87%.
Okay. So, can someone interpret that interval for me? It's gonna start with a statement such as, I am 90.
57.5.
Proportion me was between.
Yeah, the population proportion is not mean. Mean is something else. Yeah, the population proportion is between 57.13% and 72.87%.
Now,
Yes.
since I go all the way through, going from standard error to margin of error,
Yeah.
my end was 0.07869, not 854.
Point zero. Wait. Point zero.
No, for the margin of error.
Okay. What'd you get for the confidence intervals? Close to this.
I got 57.1 and 72.9.
Yeah, that's
Just
good.
about right, right? So that's fine.
Yeah. Yeah. And you
Your
just keep it all in your
10%
calculator.
that you want.
And that would be even easier, because you won't have to round at one point.
No, 99, 100%, right. Okay.
Just do it like this. And the confidence interval, all you need is this.
to split it up between the two sides.
Percentage of the
Yeah, you can call this percentage.
Because look at the
Yes.
figures.
We can do one of two things now. I can just preview the next subject and then we can take a break. Or we can take a break now. Take a break now? Break now. Alright. I can share.
Barbara.
As I say, how long a break do you want? It's up to you.
Yeah.
One, Richard votes for 1 minute.
Who's that?
Should we just go 10 minutes, our normal 10-minute break? Alright, let's come back at 8:17.
Because I didn't get it.
Oh, it's okay, one time.
Nah. Just divide it.
It's easier, because it's the exact same thing. It's just this superimposed. Good, excellent.
You don't do bring some money with you.
Easier way to find
That,
score. You can do it just click on
I get it now.
you get it?
Yeah.
It's easier.
Don't worry
because
about
it's
that.
different.
No, I get it, I get it. I just want
And there's really only 3 of them. 1.96, 255, over 99%. It does get a little bit more complicated when we do 1 tail. That way.
Fair enough. Fair enough. Fair enough.
Question, Victor?
Yeah, I was confused about how we got to 1.6, but I got it now.
You got it?
It's because it's one, so I counted for one tail, not the two tails.
Okay.
I'm getting 95%. 1.65. Because there's only one.
That means there's gonna be, this is gonna be 95%,
Now, if you get
95%.
you have 1.6.
Right.
Yeah.
But if we get a two, then it will be like another 5%.
Wait. No, we're just looking at, so we're looking at 90% confidence. That means 5% of this side,
Yes.
5% this side.
Okay, so now I can.
So, there's
That
5%
number that
this side. How much is gonna be?
476, you want to multiply that.
95%. Well, what do you know, 1.65. There's gonna be 5% this side, that's just
Is the number
5%
that
in
you're gonna
that
say
area. That shaded area.
1.65 plus or minus, and that's how you get this bar.
Got it. Bingo.
It's a miracle that I know this.
right now. I don't know anything else.
You get why we get 1.65?
We gotta add it, right?
I don't know.
Yeah, it's because it's two sides, because the Z-score table only accounts for one of the tells, not for two, and 90% would be,
Speak to me in English. 'Cause I don't.
what,
What, yeah, explain, show me.
I don't know if he explained it like that, but that's the way I got it.
So I can show you. Explain that.
Yeah, you see that.
I just figured I'ma just add it.
Right, but we're gonna just add it.
Look at the reasoning.
The reason is that, so, got here, the bell shape, whatever.
Mhm.
Oh, yeah.
So you say that the confidence interval is
You fucked the
90%.
clip?
Right.
This is the confidence interval, 90%.
What's that?
So that means there's 5 here, 5 there. But the Z-score table only reads one,
I'm not
one
getting
end, so it doesn't read two of them, which is why we find here 1.65,
You know why? Because somebody had an iPad Plus and they were
because it's not accounting for this side. So 1.65, it says 95%. So 1.65.
You know what? I had to update my phone.
Yeah, that's 95.
It's in
The entire thing, no, yeah, I know, it is
Oh, the
5%.
side, inside, gotcha.
Because you see how it's only saying one side of it is not accounting for that one.
Oh, gotcha, gotcha.
Which is why I was always
I got it.
confused, how do we get 90%? You know, 1.65 is not, you know, and then I realized that, because it's only accounting for,
That one side.
yeah, that one side, and
Oh, you're not.
here, you just gotta pretty much,
Yeah. You got
5%.
maybe that's what
The extra 5%, that's why it's not,
That's what he was saying, one side.
yeah, one side, yeah.
Okay. And then, so just moving forward, just always get the two, the one at the top and the one to the bottom, correct?
Yeah.
For the Z-score.
So, for example, if we wanna find out, 80%, what is equal for 80%?
It'd be,
So-
20, right?
Right.
Divided by 10.
Yes.
So we want to do whatever's closest to 10%, which would be, oh, yeah, you did.
Yeah.
Please, hold on.
I think it's the same thing anyway.
Okay, so, oh, right here, so it would be this one, right? The 0.0985?
Yes.
Okay, so then the Z-score would be 1.29.
Yeah.
You're a genius. You get it? You get the, how to get the Z-score yet?
Yes.
You sure?
Yeah. I just had to figure out, my decimal point was off, and
Oh.
I could work back to figure out how that happened.
I need to take my quiz right after class.
Yeah, me too.
Alright,
Can you see the quiz? I can't see it, trying to be like what I got,
What you
what I
got?
got wrong.
Click your score. Click on your score and it's.
Andrew, you see the paper I posted?
This is class?
Yeah.
Yeah.
Oh.
Oh, you did
Is
that?
there any free computers
Yeah, thanks.
next door?
I printed it up too, I'll show you.
Can I have your paper for next time you stop?
It was a trick question, that's nice. Huh.
I had to
You
do,
put everything together.
it took me, just took me a little while.
So hold up,
I had to do an
did you
introduction
get the
and a
answer right?
conclusion, because you know,
He's making it wrong by how you word it?
yeah.
Yeah,
He should
he
do the
doesn't
first
get partial
one.
votes. Wow. So he doesn't give it. So,
Confidence.
I think everybody got that, I think we should give it a curve.
That's what I did, was introduction. I had to read every single one of your paper, put it all together in there.
This is Victor's question. You went together, but we're taking turns, so you've done already? Putting the paper together.
I was like, hold up.
And I was approved for you.
That's fine.
Economics.
Oh, my computer's not working.
Is it turned off by accident? Is it off?
It's
Yeah, it
one
says
page
like
paper
it's-
from all of us.
It's
But it's
not
just
connected, you
because
check the
it's a
wires, but I
group.
can touch every
It's a
wire.
group. So everybody writes
Is
one
it powered
page.
on?
The
This
one
system
person
actually
needs to put it
powered
all
on?
Oh,
together.
yeah.
So Victor put it, we're doing four, so Victor took the first one.
Cause it was on and I
Now,
pressed
next
something
week,
by
somebody else
mistake.
is gonna do put it together. And putting it together, you have to write visual cover, intro, abstract, sources, and a conclusion. And we have all that, you want to put it together.
I think it's better if, like, are we gonna meet next Saturday? See, so for the next case, it's better if we,
There it goes, coming up.
we read our case before we come this Saturday.
That's
So
IT.
that way
Well,
we're
wait,
Next time you have a
because
problem,
when I was doing
What's
the
your
case,
presentation?
there were a lot of ideas, and you know,
that once a
every
year,
single idea was
that twice a
different.
year.
We can all
Brian
come
was about
together
to take it
and
from
say,
me
hey,
yesterday.
we use those ideas for the next person, we put it in together. For a case, you have to present an argument, say why you think that we can do that better. Yeah.
This is the part, taking breaks,
We're
is
not-
You
not
guys finished the
just.
second case already?
I'm writing it, you know, I'm almost done.
We just did that. Well, obviously, we can, let's start the second case. What's that quiz? When do we
It's
see
given
this?
this one on Thursday.
On Thursday, it's taken.
We have to- But it's a take home.
Yeah. Okay. You broke it.
What class you taking?
This, same with you, and I'm taking communications.
That's the communication.
Operation.
You dropped it.
But I'm still up.
Oh, you cut around.
Show the boss.
But I want you to say what it says.
It says it's not connected.
Oh,
Input signal.
the display.
I think, cause I pressed like a button here, I don't know.
Did you press that button in the thing down there?
It's a button.
Power button.
No, it's power.
So, yeah, all these computers have the same problem. And, it's the cable.
I don't know, like the date. I know it's not.
It's the computers. I tried to fix it for you the first time, and you ruined it.
This is the first time.
No, this was the second time. I fixed it once already.
When? I don't know.
And I said, and you also get
Oh, no, it ain't, you didn't get it, you just powered
Yeah, I tried. That again, argument?
Yeah, but the thing about question one,
Yes and no.
Okay. There's actually only press that we have mistakes on that. I'm not worried about it.
And we got, Monday night section, we got a bit early, we're a little bit behind. They're not as lively. They don't
I
ask as many.
think what the check mark is the right answer.
they're in shock.
Sorry. They're trying to, no, that's good, I like it. With the Monday night, I have to read it, is there a little bit of pain on their face, or?
Yeah, at
Or
least
a
we
lot
tell
of
you
pain?
straight up.
A little bit of pain, we keep going, a lot of pain, so.
I just don't get it.
Okay, so it's like only class.
What?
Well, yeah.
Every other class.
The other class, you like read the
Working on the paper. No, he's working on the paper of his, something else. Some other work.
Alright, let's go ahead and get started again. We're now going to move on to mean differences. Good news is this is very, very easy, yes, very, very similar to the first thing we did, which is proportions. We're gonna use the sampling distribution of sample mean differences the same way we use the sampling that whole thing. The properties are all the same, the confidence intervals are all the same, so that's great. So in terms of mean differences, suppose we have two populations and we want to try to find the difference. We might have the average amount that a Yankees fan spends on Yankees gear, and the average amount of money that a Red Sox fan spends on Red Sox gear. So we have Yankee fan $670 per year, per season, and maybe a Red Sox fan might spend, I don't know, $490 per year. Alright, so that's our sample average. So we need to know the difference between these two. Well, we have a point estimate. 670 minus 490 is, what, 180? Yeah, 180 would be our guess for the difference. Alright, 180 would be the difference. But that's just a guess. I mean, it's not a guess, it's a sample. So we need a confidence interval to say how confident we are that that's the difference and that there is a difference. Now, we already have some skills to do this. We're going to learn a couple new formulas, but we already did this, I think, in class 2, right? We could take this 670 point estimate for a sample, and we could construct a confidence interval for it, right? And we might get, I don't know, 651 to 692. That might be our confidence interval, and we do the same thing over here. We could go for 478 to 502. That might be our confidence interval. But that's a lot of numbers, and there might be some differences in the way we sampled these two. We might have asked more Red Sox fans, we might have asked fewer Yankees fans, and the standard deviation of the population of Yankees fans might be different than in Boston. Everything's so tight and compact, and everybody in Boston is the same, right? But we have more diversity in New York. Any of that kind of stuff could have been going on. So instead of just pasting together what we already know, let's just look for statisticians to guide us on this and tell us a formula we can use to make this a little bit more simplified. And they do this by giving us properties that are familiar, will be familiar to you. And they will call it the sampling distribution of the sample mean difference. Does that look familiar? Alright, all we did is we put sample mean difference in for the other two things we've tried. Predictable sampling properties, sampling distribution properties, and we can use those predictable properties to build a confidence interval. So, suppose we were to take a bunch of samples of Yankee fans, a bunch of samples of Red Sox fans, or actually, suppose we were to take a sample of Yankees fans, sample of Red Sox fans, find the difference. We were to find one difference, we're going to do it again. Another batch of Yankees fans, another batch of Red Sox fans, find the difference. We do that over and over again, put all those in the frequency distribution. What's the frequency distribution going to look like? Very good. It's going to be a normal distribution. And we're going to call that the sampling distribution of the sample mean difference. Probability distribution of all possible values of sample mean difference. So this little x bar, this is the mean of population 1. X bar 2, the mean of population 2. Sample size of n is taken from one population, sample size of n taken from another population. Alright. Now remember this little u figure? We call that the mean of the whole population, mu. Exactly. And the true difference between the two populations is mu1 minus mu2, just one minus the other, the difference between them. We're going to calculate a point estimate. Sample mean 1 minus sample mean 2. And again, we're going to do that 100 times, 1,000 times. We're going to put it on a frequency distribution and call it sampling distribution of the sample mean difference. And that's going to be normal. And we're going to know each and every time we do it. Each and every time we do it, there's going to be a 95.5% chance that our sample mean difference is within 2 standard deviations of the mean. We're not just confined to 95.5, we can use any confidence level we want. Start at 0, go up to 100. Or not 100, 99. Alright, there is, alright, as long as normal sufficiently large samples, we'll define sufficiently large as 30 or more from both samples. It's going to be centered around the population mean difference. So the mean of the sampling distribution of the sample mean difference is going to be the mean of that mean difference for the whole population. And that's what we'd expect. You know, we don't know the difference between how much Yankee fans and Red Sox fans spend on sporting gear, but God knows, and God knows exactly what that is. We are most likely going to hit that number. Sometimes you're going to be a little high, sometimes you're going to be a little low. And there's going to be a standard deviation. The more extreme edges of the standard deviation are going to be less likely because we're going to have a sample size. So the standard deviation of this sampling distribution, the sample mean difference, is going to be smaller than for the parent population. And we will use this formula to crank it out. Notice n, sample size population 1, sample size population 2 is in the denominator. So the larger those are, bigger number in the denominator makes this smaller. And this is population standard deviation. The bigger that dispersion is, the bigger this is going to be, the bigger that dispersion is, the bigger this is going to be. And we take the square root of the whole thing. So it gives our beautiful bell-shaped curve centered around mu1 minus mu2. Predictable standard error.
That's what that means.
That's what it means?
And this one is-
Oh yeah, this is the standard error. This is the standard error. Now you remember, I said we already have some tools to construct confidence intervals for each of these individually. Now we have a tool to construct a confidence interval once we combine them. And it's not that different than if we were to just guess and just paste together what we already know. Confidence intervals. How many of these standard errors do we need to add to and subtract from our point estimate? Well, it depends on how confident we want to be. We're going to choose an appropriate z-score, and we're going to plus or minus that number of standard deviations, or excuse me, standard errors. This little sigma sign, that is population standard deviation. Now if you remember from our study in class 2 that if we do not know the population standard deviation, we have to use the sample standard deviation, which is going to be a little bit bigger, right, Miguel?
Mm-hmm.
Just that account, the fact that we don't know certain, count for the unknown. We also, in the case where we did not know population standard deviation for means, we used a t-table. Alright? In this case, statisticians are okay with us using a z distribution.
So confused.
The reason why is they say there's so many moving parts, right, that you could be off a little bit on this one, you could be off a little bit on this one. Chances are it's just going to average out to something predictable. There's more numbers involved, and with more numbers involved creates more randomness. More randomness lends itself more to a normal distribution.
Even mathematicians the best job because we just make stuff.
So mathematicians are okay with this. Now, if you like, you could use the t distribution. That would be correct. You could use that on any quiz, anything in the real world. And I would say, oh, you want to be really, really accurate. That's fine. But you could also just use the z distribution.
Can you go back and explain what the bottom line difference is between the z and the t tables?
Yes, absolutely. Absolutely.
Thank you.
So we've been using this example the whole class that if you want the chances of your sample mean difference being within 2 standard deviation of the means is 95.5%. All right, so suppose you want to be 95% sure.
Okay.
All right, that means you need to go plus or minus 1.96.
Right.
Now, that is if you know the population standard deviation. You know what it is.
Okay,
If you don't know what it is, then you need to make a couple adjustments. One, you need to calculate it yourself and make it a little bit bigger. And the other thing is you need to go a little bit further than 1.96 standard deviations. Question is, how much further? Well, you look at the t-table, because that gives you a little bit extra cushion. Tells you how much bigger you need to make your confidence interval to still be 95% confident. And so the t-distribution may tell you to go, instead of 1.96 to 1.984.
okay, so basically the bottom line is the t-table is gonna give you a margin of error for accuracy, and the z-table is gonna be more specific.
Yes.
Okay, thank you.
Fantastic. All right. Let's do a couple examples. Turn to page 290, exercise 8.6. Oh, righty. Oh gosh, this one gives me a headache.
Yeah.
I don't want to hear this.
All right, well, it's just all these words at the beginning. So we've got two microwave transmitters. We've got design A and design B. All right, and we've got error rates for the two designs. All right, so we do a sample of 50 for design A, and 50 for design B. All right, thank God. We take 50 of design A and 50 of design B, it's the same. And we find that the error rate for design A is 22.3, and the average error rate for design B is 17.6. All right, so design A seems to be making more errors, right? So that could be a problem. We like design B better. But can we really say we like design B better? Maybe there's a margin of error we need to account for, and the difference isn't as big as we think it is. And maybe we might even find confidence intervals that overlap, such that we can't even conclusively say that design A is making more errors. So let's find the confidence interval for the actual difference. Our point estimate difference is the 22.3 minus 17.6, which is,
4.7.
how much, 4.7? Okay. So our point estimate is 4.7. But we need to add some standard errors to that, a certain number of standard errors, and see what we come up with. So that 1.65, where do we get that number? Yeah.
90% confidence.
Yes, you've got it. We decided we want to be 90% confident about this. So we decided that we need to go plus minus 1.65 standard errors. And we now, luckily, have a formula for standard errors. It is that exciting formula we saw in the previous slide. Standard deviation 1, standard deviation 2 squared, divided by population 1, population 2, square root of that whole jump. So, yep, we know the standard deviation for design 1 is 5.3, standard deviation for design 2, 4.6. As you can see, we square those, divide by 50 each, square root of all that, and
I'm confused again why we're using 1.65, and I'm
So-
sorry.
So am I.